this. Sorry, I accidentally recorded it to the web, so that's horrible because it takes 45 minutes for them to send me an email, so this is better. Okay, good afternoon, everybody. So this week, what we have due is, if you haven't already taken a mock exam, take one. If you have taken a mock exam but changed something, like you're moving to a new location, you didn't test your internet, something like that, there's one open today until 6 p.m. and one open till tomorrow till 6 p.m. from 8 a.m. to 6 p.m. tomorrow. So if you feel confident everything's working, that's great. I gave a top hat exam with Proctorio on Friday. I had one person had a couple issues, but they just restarted their computer and everything worked fine. So that was like 65 people. So I think we're good to go if you've done your mock exam. Okay. Today we're going to go ahead and review for our first exam chapters 1 through 7. I think it was wrong on the email. It said 1 through 6. It's actually 1 through 7. So the review I've posted on Canvas and the review I'm going to go over today are both say chapters 1 through 7. Okay. Our exam will be today, Wednesday, at this exact same time. Do not log into Zoom. Just go straight to Top Hat, get everything set up. I'll send you instructions Wednesday morning about rebooting your computer, what to have, what not to have. And so, and then what the AI is looking for is basically suspicious behavior of looking away too long or talking in the background. So the idea is that the AI does all this instead of the live proctors at Examity or other live proctors where they'll yell at you. Nobody will yell at you. So you just need to go ahead and relax, take the exam, and go ahead and do that. After the exam on Wednesday, I'll go ahead and look at the class average and scale as necessary. So don't worry about the raw score you may see on Top Hat. I will be going ahead and scaling that, curving it if needed to get the class average I'm looking for. Okay, so don't worry about that. And then go ahead and start reviewing chapter 8 for Monday. Okay, I have a question here in that. What do you mean change in location? I mean, if you had your mock exam at one house and then you've moved or plan to take it at like the library, test it where you plan to take the exam. Okay, it's because different Wi-Fi's and different speeds and stuff. So that's what I mean. Animals do not trigger the AI, the barking and meowing. It's when people start talking to you saying, answer C. That's what it's looking for in the AI. So, and again, nobody sees these unless I get a big flag saying, suspicious behavior, then I will review it and figure out whether or not it's considered suspicious. So, but it's no live person. Nobody's going to steal your ID. Nobody's going to write down your information, as may have happened on other sites. So I really like this platform because it's so more relaxing than other testing sites. So. But that's another reason for the mock exam is to get really comfortable with the platform so that all you're worried about is getting your good answers on the page. We did have some issues where the connection got a little weird at the end, and so submission was a little weird at the end. But that only happened to one person, and that's because they changed locations, which is why I suggest doing your mock exam exactly where you plan to be taking your test. Yes.
So I was asking about the change in location. I'm actually quarantining at my boyfriend's apartment. We both got COVID. I'm trying to go back to my apartment tonight after I get retested, but I won't be back until after 6. So could I get an extension for that? I'm sorry.
There's another one tomorrow from 8 a.m. till 6 p.m.
Okay, perfect. Thank you so much.
Okay. So I want you to have zero stress about the exam. I want you to worry about just trying to get all the stuff you studied in your head onto those questions on the exam. Okay. So again, no Zoom class on Wednesday. Just go straight to Top Hat and do your thing. All right. Questions about that? Okay. Can we have scratch paper? Will that trigger the AI? No. Okay, 3 things you'll need for the thing. You'll need scratch paper and a pencil. You do not need a calculator. There will be a periodic table at the beginning and end of the end of the exam, so that you can scan up or scan down to get to that. That's the only reference material you need. You may have scratch paper and a pencil and you'll need a picture ID. It doesn't have to be a school ID or a driver's license. It has to be one or the other, and it has to have your picture on it. And what's going to happen, what happened once was that they tried to scan the picture and they were wearing glasses on the ID and they weren't wearing glasses at the time. And the AI said, no, it's not the same person. So whatever your ID shows you wearing, please wear that. Like if you're wearing glasses on the ID, wear glasses. If you're not wearing glasses on the ID, just take them off to get the facial scan. And that usually eliminates that problem. But it's pretty good. It's a pretty good scan because it'll pick that up. So, all right, any other questions about the exam?
So we won't have any access to like the PKA tables or?
Yeah, correct. If there's a question where you have to figure out whether it's shifted one way or the other, I will give you PKAs. Other than that, you need to know that general trend of where alcohols are, where water is, you know, where all the different kind of hydrocarbons are, and acetic acid. You know, so there's about 5 that you need to know, and those are kind of highlighted in the goals. Okay.
Okay, thank you.
So another thing about studying, okay, so a good place to start is to look at the review that I'm going to go over today. The review that I'm going to go over today these are the big ticket items for those particular chapters. The second thing I would do is go back to the goal slide. Look at the 3 big goals. Make sure you understand what they are and how they kind of link together. And then if things are, you know, if all that's going really well and you want to get that extra, you know, little bump to get the A, go ahead and look at the longer stuff and add the details in that are above and beyond the review and the goals. The goals will get you part of the way there. And so, but that's what you need to study first, and then start filling in all the details around that. The test is predominantly multiple choice. And in fact, it's 100% multiple choice, or there is no open response on this particular thing. And there's no drawing on it. And unfortunately, in class, I'd have you draw, but I make up for that by having the activities. Yes, the review is on Canvas. So I make up for that with the activities where you get to draw stuff and upload them. So you get practice drawing, but we don't have to, you know, do some finicky thing online where it'll count it wrong if you have, you know, the atom just slightly out of frame or whatever. So I prefer to do the multiple choice on the exam. Okay. All right. Any more questions on the exam? You should be confident you understand how the exam is going to go, and then get confident on the different subject matter.
Is the homework also a good thing to look at, or is it going to be different from the homework?
The questions are designed to be like the homework questions, but not the same as the homework questions. So if the way the questions are asked, like what is the least of this? What is the most of this? Those are the types of questions. I'm using the exact same form at which those questions were asked. They're not the same questions, but they're the same form and same topics. Okay?
Okay, thank you.
Okay, so I'm going to do 2 things for review first, and then I'm going to open it up to other questions. The first thing I'm going to do is the review from chapter 1 through 7, and I don't have 7 on this one, do I? Ha, ha, ha. Okay, so I'll have to pull up another one. Let me pull up something else here for I usually transfer this to my iPad, but I'll have to do 7 separately because I don't have it here. Okay, so let me just go ahead and do 1 through 6, and then I have another review on Canvas. It's called SN1, SN2, E1, E2. And it's just 5 slides. It's kind of a condensation of all that stuff. And it gives it back in that last little table, you know, this is like the net summation of all of those ideas. Okay, so I'm going to go ahead and share my screen. And if you have any more questions, go ahead and put them in the chat or chime in. Okay, I'm going to move my thing over here. So my gallery mode's over here. So if you're raising your hand, I can glance over here. Okay, so let's see. So you can see my screen hopefully here. It's the organic review. So chapter 1, the big thing we learned in chapter 1 was the types of bonding we have, okay? Sigma bonds, pi bonds. But we also learned about hybridization. Hybridization controls many things. It controls the kinds of bonds we can have. For example, sp3s make sigma bonds. sp2s make sigma bonds but have an available p so they can make a pi bond. SPs make sp bonds, but then they have 2 p orbitals to make 2 pi bonds. So that's very important. And because of those locations right here, we also have shapes. And the shapes are determined by electron regions, not just where atoms are, okay? Electrons take up space. So when you have a lone pair, for example, in the case of nitrogen here, that takes up space and that controls the geometry, okay? And in water, this takes up space and controls geometry. So don't just look at the atoms when you're thinking about the shape of the molecules. You have to look at the Lewis dot structure and look at where the electrons are, okay? So what we also learned in chapter 1 is the different general functional groups. And we're gonna hit all of these functional groups before the end of the semester. And in fact, we're probably gonna start hitting alcohols and amines next, okay? So up to now, all we've really done is alkanes and a little bit of alkyl halides, which is chapter 7. But what we're gonna end up doing is we're going to end up going through all of these next functional groups in the next few chapters, okay? So the ones you really have to know are the alkenes, alkanes, alkynes, and what they look like, okay? So this goes to one of the questions that we had about pKa. Knowing this general trend of pKa, where we have the sp3s, where water is and alcohol are about the same, and then where we have the strong acids down here, and then acetic acid, which is here, okay? Then knowing that where alkenes and alkynes are on this table, that's the critical factor on this. Now, we have a hybridization difference between those, which is what changes their pKa's. So knowing this relative ratio right here is very important. Knowing that alkynes are more acidic because of their hybridization. Alkenes are more acidic than alkanes because of their hybridization. And alkanes are the weakest acid we deal with because of that hybridization. Okay.
Sorry, you said this is posted on Canvas, right?
Yeah, the actual one with the all 7 chapters is posted on Canvas.
Okay.
Yeah, and if I'm wrong, go ahead and tell me. I'm pretty sure I posted it already. So the other thing about acids and bases is the idea that we have different definitions, but they all fall under the concept of Lewis acid, Lewis base, okay? So if you can remember, Lewis acid is an acid because it can accept a pair of electrons to form a new sigma bond, then that applies to Arrhenius because the hydrogen and the water are there. This video will be posted just like all the others on the YouTube channel. Oh, also in the announcements, I put in a link to both the long videos and the lecture videos are also on under the announcements tab under our Canvas site, by the way, just so that makes it easier if you don't have to remember it. If you haven't already subscribed and get chimes on it, then you'll be able to see it there. Okay, let's go back to Lewis acid and base. Lewis acids accept a pair of electrons, meaning that they are lacking electrons and are looking for electrons to make a sigma bond. A Lewis base donates an electron pair to make that new sigma bond. So when you draw your Lewis dot structures, if there are lone pairs on it, start thinking, hey, Lewis base. Okay. Now, so that covers Lewis acid and Lewis base, and that's how it adapts with Arrhenius. We don't typically use Arrhenius in our things, but the next most important acid and base concept we use is Bronsted-Lowry, okay? And the most important concept of Bronsted-Lowry is that when an acid donates its proton, it becomes a conjugate base. Okay? So when it loses its proton, it becomes a conjugate base. Okay? When the Lewis base accepts the proton, it becomes the conjugate acid. Okay? So that is key. Now, to know which way the equilibrium lies, all you have to do is compare the pKa of the acid on one side and the conjugate acid on the other. Whichever is the weaker or higher number, the equilibrium shifts toward the weaker acid. Okay, so that is the most important concepts in acid-base. Make sure you can do that acid turning into a conjugate base turning into a conjugate acid, and compare the pKa's of the acids to figure out where the equilibrium lies. All right, questions on chapter 1, chapter 2. Hybridization, Lewis acid base in general.
I have a quick question. So if let's say like if you were looking at the pKa's, if let's say like the acid on the left had a pKa of 3 and the acid on the right had pKa of 2, the equilibrium would shift to the left?
It would shift to the weaker acid, the one with 3.
Okay.
Because there's not that much of a difference, it's going to be shifted that way, but it's not 100% that way. So
okay.
It takes a big difference, like greater than 10 points, to have it 100% shifted.
Okay, that makes sense. Thank you.
So, but if they're close, it's still shifted, but not 100%. So just keep that in mind. Okay, good question. All right, well, let's move on to chapter 3. And this is chapter really 3 through 6, because we actually did nomenclature on that. And so the important ones here are the ones in the box. We haven't done arenes yet. We're going to do arenes in a couple weeks. But up to now, we have learned about our hydrocarbons, anything with carbon hydrogen on it. We've learned about our saturated hydrocarbons with no double bonds and only sp3 hybridization. And then we've learned about our unsaturated. And we learned about our unsaturated that they have different parts in the name. The infix tells us the difference between an alkane, an alkene, and an alkyne. So that brings us to some of the common groups that we have these are common substituents that you'll need to know the names of because they are so commonly used in our nomenclature. So the first 3 are very simple because they follow our rules. We have the meth, and then because it's a substituent, we add the YL, so it's a methyl group. Second one, eth, propyl. We don't have any isomers associated with these, so they're except for the we have the isopropyl group. Once we start branching at that 3-carbon chain, we now have isomers, and they have different names. So if it's straight chain, it's propyl. If it's got a Y in it, it's the iso. And the butyl does the same thing. Straight chain, iso is where it has this Y at the end. Sec is where the methyl group is moved over. And tert is where you have 3 methyl groups all on the same carbon. So knowing the difference between these common alkyl groups is important. So this is a laying out all the rules. In fact, this has all the rules for E and Z and R and S, okay? So these are all the rules and they're in order. So find our priority, find the longest chain, try to get our numbering system to the lowest if at all possible. Remember that if you name it for something like an alcohol, it has to have that functional group be the lowest thing. Identical substituents use di, tri, and tetra, but you do not use those in alphabetization. Try to alphabetize everything and then determine whether or not you have stereochemistry. If you have a double bond with 2 or more substituents, E and Z. And we use those 3 rules of prioritization. Atomic number 1 carbon over, and if necessary, double and triple bonds. Okay. We can use cis and trans if you only have 2 groups, but E and Z works for all other systems, or even with 2 groups if you want to be precise. And then don't forget that R and S. R is clockwise, S is counterclockwise. Okay, okay. And again, we have those parts of the name. We have the prefix, which is number of carbons. And we have all the substituents are before the prefix, right? Because this prefix, infix, suffix is actually the last word in your sentence. It tells you about the compound. So number of carbons, the infix tells you whether you have single, double, or triple bonds. And the suffix tells you whether it's just a hydrocarbon, because it'll have an E at the end, or if it's something else, like an alcohol, OL, or one of the other functional groups we've learned. Okay. And so knowing that is going to be, it's very helpful in your nomenclature, and it's kind of built into the nomenclature rules in the previous slide. Okay, and again, when we have our single and double and triple bonds, we use these things right here. And that should get us all the way through. Now, we're going to add alcohols and amines and carboxylic acids as we go. So really all we need to know right now is our alkanes, alkenes, alkynes, and our substituents. Remember, alkyl halides. Halides are always substituents. They never change the name. Okay. So that's nomenclature, and that's chapter 4. Any questions on nomenclature before we move on? There's even a little bit of chapter 6 in there, which is the RNS. Okay. So you can use the chat if you want. Okay. So that brings us on to chapter 5. In chapter 5, we actually learned about cis and trans, and we learned about E and Z. But what we also learned was once you have a double bond, once you have that pi bond, it's the most reactive bond in the species. Okay. And most of the time, what happens is something will add across that double bond, meaning you have two atoms, one atom's going to be on carbon 1 and one atom's going to go to carbon 2. Okay. And so because of that, these are addition reactions. We're going to take away that double bond and add 2 new sigma bonds. So we can do that with acids. HCl will add across there, giving you the chlorine on one and the hydrogen on the other. But don't forget, you have to know where that hydrogen is going to go. Okay. And that hydrogen goes on the more hydrogenated side. More hydrogens gets hydrogens. Remember, that's the Markovnikov's rule. So don't forget the Markovnikov's rule and associate with additions across alkenes. Okay. Now, if we didn't add an acid across, we added water. Well, that's called hydration. We get an OH on one, the hydrogen on the other. And it follows Markovnikov's rule. Okay. With halogens, where you have 2 halogens, one will be on one carbon, one will be on the other carbon. But remember, that adds anti. There's the other one adds to the bottom after forming that 3-membered ring. Okay. Hydroboration seems to add backwards, but it turns out boron is the more electropositive atom. And so it seems to add backwards, but it does actually add correctly, and it does follow Markovnikov's rule. And then there's hydrogenation. Now, the hydrogen bond is not polar. So we have to activate it. We have to activate that by adsorbing it to the surface of a metal. Once it's on metals, so it has to have a catalyst, then it can add across that. And because it's at the surface of a metal, it always adds on the same side. Okay. So questions about the reactions associated with alkenes. And these are the only reactions we're going to deal with in this. All right. So the other thing we learned about in chapter 5 was the beginning of the idea of mechanisms, basically looking at what's happening at each stage in the reaction as we go from starting materials to products. Okay. And we use what we called reaction diagrams to tell us what's happening. Okay. So in this case here, we have energy and we have basically as the reaction progresses. It's not true time, it's just like what's happening in the reaction. And so we have our starting materials. We have to know what this energy is to get to that transition state. That's called the activation energy. The transition state is that momentary point in time where the new bond is forming and the old bond is breaking, okay? We can't isolate it. It doesn't really exist except for an infinitesimal point in time, and that's our transition state. And then once our old bond starts moving away, we cascade down to products. Now, if the products have more potential energy than the starting materials, then we have an endothermic reaction, meaning it took heat to do it. But in this case right here, we actually have less potential energy, meaning it gave off heat or was exothermic. Okay, so those are all the different components found in your reaction diagram. And so make sure you understand each of those steps in that. Now, what if you form a carbocation? If you form a carbocation, that's now a two-step reaction, okay? And therefore we have a slightly different system here. And the big difference here is you have what you call the intermediate, okay? This is something that can be isolated or at least viewed. We know it exists because we can actually see it, okay? So that's the difference between transition state, is this theoretical state we can't see, and an intermediate. The intermediate we can see. So, but we still take an activation energy to get to that first transition point, then that's going to give us, in most cases, in what we do, it's typically a carbocation. And then the other thing that has to come in and react with that carbocation is this second activation energy, which gets us to our next transition state, starting to form that new bond, and then cascade down into products. And again, we have endothermic or exothermic. But the key is we have two humps and we have an isolatable intermediate in the step. So, so we can easily tell the difference between them by looking at that diagram. Questions on the coordinate diagram or reaction diagram? All right. So am I muted? No, I heard people, so it's not you. All right. Okay, so that being said, when we look at mechanisms, we see that there are 5 common patterns that we should see, okay? So in an acid catalyzed system, we're probably gonna add a proton. In a base catalyzed system, we're gonna take away a proton. If we have not really anything with a positive or negative charge in it, now we have to start thinking about Lewis acid, Lewis base. Our electrophile is our Lewis acid. It's looking for electrons. Our nucleophile is our Lewis base. It has electrons to share, and it's looking for something with a partially positive charge. And when they interact together, they form a new covalent bond. So that's our third pattern. Our fourth pattern is most commonly used with carbocations. If it can form a more stable carbocation, it will. And so we see that happen. And it always happens in that intermediate state when that carbocations form. And then the last thing we have is pattern 5, where we actually break apart to form a stable molecule or ion. Now, this is the thing that happens to make the carbocation. Let's say you have an alkyl halide and you break that bond to form your carbocation, that's pattern 5. Okay. Now, once it's in the carbocation, it can undergo pattern 4. And then when the Lewis base comes into interact, that's pattern 3. So these are the 5 patterns that we will see in our mechanisms time and time again. All right, questions on patterns? Okay. So carbocation stability. Okay. So 3 carbons on carbon is more stable, our tertiary carbocation. Okay. So that is 3 carbons on that carbon. It stabilizes it by inductive effects, right? So all the carbons can donate a little bit of electron density, making that a little less positive. But don't forget that a carbocation is trigonal planar. So we have one sticking out here, one going in here, and we have an empty p orbital. There's 0 electrons in that p orbital. That's what makes it the carbocation. Okay? And that controls our products because you can have your Lewis base come in at the top or the bottom. Doesn't matter because it's symmetrical. Okay? So don't forget that your carbocation is that sp2 hybridized with an empty p orbital. So as we go to secondary, primary, and methyl, these are very unstable and we hardly ever see them. So when we start talking about the mechanism of different reactions, and we say we have a primary alkyl halide, we're probably never going to go through a carbocation underneath. Tertiaries form very stable. They're probably always going to go through a carbocation intermediate, which means this is the only one we have to play with. And we look at stability and solvent to tell us the difference. Now let's talk about rearrangements, okay? You can only rearrange to get a more stable carbocation, okay? If you formed a tertiary carbocation, it will not rearrange. You already have the most stable carbocation. If you form a secondary carbocation and can transfer to a tertiary carbocation, at least the majority of your product is going to be that rearrangement, okay? So in this case here, we start with a secondary carbocation, and we can move a methyl group, just a methyl group, CH3, or a hydrogen. Those are the only two groups we can move, okay? So we can move a methyl group or a hydrogen to give us that more stable carbocation.
I have a question.
Yes.
In the homework, you had a secondary carbocation move to a secondary benzylic ring carbo. Is there any limitations to that? I mean, like how many carbons off the ring the carbocation originally is, or anything like that? Because that one caught me off guard.
We're going to learn a little bit more of that in chapter 9. In chapter 8, when we talk about arenes. Turns out that, and this was in the book, but I didn't discuss it specifically in class. The carbocation, if we form a carbocation next to a benzene ring, this is actually more stable because this has a lot of electron density to help stabilize the charge. So if you can ever put a carbocation on that one carbon off a ring, it's even more stable than a tertiary carbocation. But we'll talk about that more in another chapter.
Okay, thank you.
But it really wants to be that carbon right next to the ring, which is called that benzylic carbon, that first carbon off the ring. Okay, so, and then this brought us to the last chapter we discussed, which was stereoisomers. And stereo is 3D space, and so we ended up having to define the idea that we have different types of isomers. And isomers are just compounds with the same molecular formula. We have constitutional and conformational isomers, which are just hooked together differently or drawn differently. But then we worked a lot on stereoisomers. And these are things that are, if you have one stereocenter and you have non-superimposable mirror images of them, that is a pair of enantiomers, okay? And we learned how to figure out which is R and this is S, and we learned how to draw them going from one to the other, so we have that pair of enantiomers, okay? Now, if you have more than one stereocenter, then you have diastereomers. And then you can have as many diastereomers as diastereomer pairs as centers 2 to the n. So if you have 3 stereocenters, that's 2 times 2 times 2, which means you have 8 possible isomers. Okay. So for 2 stereocenters, you have 4 possible isomers. Now, that whole set of 4 possible isomers are called diastereomers. But there's a pair of enantiomers in each of those, unless there is a mirror plane. Now, in your diastereomers, if you can find a plane of symmetry such the top looks like the bottom, that loses its chirality and it becomes a meso compound. So while this looks like 4 different compounds right here, we actually end up with a total of 3 compounds because these are equivalent and these are achiral, meaning not chiral. These are still the pair of enantiomers we started with, but because of the mirror plane, we lose that. If that mirror plane did not exist, we would have 4 diastereomers, 2 pairs of enantiomers, okay? So, and just as a reminder, R is clockwise and S is counterclockwise. This, I just found this on the internet, wasn't I? Okay, let me switch over to another, the one that I posted, which should be 7. and look at chapter 7. Okay, I'm going to stop sharing here, and I'm going to start sharing over here. Okay, so this is the one that's posted on the website there. And it's all about, okay, now that we learned about reaction mechanisms, right? And we know that we can go through a substitution reaction where it's one step, or a substitution reaction with 2 steps. If it's 2 steps, we always form that carbocation, okay? Now, there's different factors we learned about this. We learned about whether or not the attacking species is a good nucleophile or not. Good nucleophiles typically have a negative charge, and they typically are things like nitrogens and oxygens. So if we look up here, we have negative charges, we have oxygens and sulfurs. We didn't actually have any negative charge nitrogens in this one, but they are. Now, notice these are big anions right here, okay? So while the halides, these are good because they're big and fluffy and stabilize that charge and have a lot of electrons to play with. As we move down to this moderate level here, this area here, it is where we have smaller anions, and notice we start getting these conjugate bases of acetic acid here, and that's because this charge is shared over multiple atoms, it's not as strong a nucleophile. And then we have these, which are the neutral species. Now, all of these neutral species, when you draw their Lewis dot structures, they all have a lone pair. So they're all Lewis bases, and that's why they act as nucleophiles. Okay. But these are only sulfur and nitrogen that act as moderately good nucleophiles. Once we switch to oxygen in neutral state, these are what we call poor nucleophiles. They have to wait for the carbocation. Okay. So we learned that different nucleophiles can make different products. We can make alcohols or ethers or thiols or substitute alkanes just by whatever your nucleophile is. You've displaced something and you created your new species right here. And again, as you go to your neutral species, when you have a nucleophile attack as a neutral species, the initial product you form is always charged and has to lose a proton to become its final product. So, and then that's kind of summarized in this table here, right here. So if you think about your primary and secondary right here, you don't see them reacting to form carbocations. There's no SN1 reaction. There's no E1 reaction because you cannot form those carbocations. The secondary will form a carbocation, but it's not the most stable carbocation. So it works very slowly. And our tertiary tries to form a carbocation whenever possible. And so if we have weak nucleophiles, we're only going to form these unimolecular reactions. That's what the 1 stands for, which means you, whenever you see that 1, think carbocation. Okay. So if we have a weak base but a good nucleophile. So when we think about base, we want to think about hydroxide or the salt of an alcohol or T-butyl alcohol. Think of those as bases. Okay. So anything other than that, we're going to go substitution reactions because they happen faster, except in the case of tertiary. That's the only time we're going to form a carbocation because it's too sterically hindered to have it come in and do a substitution reaction. So it waits for the carbocation. Okay. If we have strong bases, but we're primary and secondary, we'll typically undergo a substitution reaction. However, once we get to secondary and tertiaries, we're typically going to go with an E2 reaction, meaning the base is going to pull a hydrogen off, 1 carbon over from where your leaving group is. Those electrons are going to kick in, and the electrons with the leaving group are going to leave with it. Okay, so that's the E2 reaction. And in strong hindered bases, think T-butoxide, primary can't undergo any elimination because there's no other carbon. So it can only go a substitution reaction, but everybody else is going to undergo this E2 reaction. The base is going to pull on a proton first. Those electrons are going to kick in and kick out your leaving group. Okay?
Professor,
Yes.
can you go over what an unhindered and hindered nucleophile are again?
Okay, actually I have another slide for that. It's also one of the things I posted on This is also on Canvas, and it's also related to this as well. So I can relate to that here. So when we think about a hindered or unhindered, we're typically looking at the substrate. So the thing with the chloride or iodine on it is what we're looking when we're doing a substrate. So that controls one thing on whether it'll do that primary, secondary, or tertiary. That's hindered. Now, when we're talking about nucleophiles and bases, okay, think about the base part is the oxygen with a negative charge on it, right? And then whatever is attached to it, if it's small like a methyl group, we would call that unhindered. If it's small like a straight chain of a thing, we would call that unhindered. But now, if you add an isopropyl group on there, so now you have two methyl groups sticking on that thing, now we're starting to get into hindered. That's partially hindered. And then our biggest one, which is 3 methyl groups on that carbon next to that oxygen negative charge, that's the bulky, most hindered base, okay? So a regular alkoxide is unhindered, an isopropyl alkoxide is kind of hindered, but a T-butyl is very hindered, okay? Or that's the most hindered base we have. We call that the big bulky base, think E2, okay?
Thank you.
Okay. So these are some other nucleophiles that I wanted to draw attention to here. We have, again, the most common ones are these negatively charged species, okay? Think about it as you already have a negative charge, you already have electrons ready to bond, okay? So they tend to be stronger nucleophiles than the neutral ones. Now, once we get to these neutral ones, draw the Lewis dot structure, you'll see all of these have lone pairs. And that's the part that is going to act as the nucleophile, okay? So when we compare, now let's think about not what's coming into attack, but let's talk about what's gonna leave, okay? Some groups are better than others. We said that hydroxide is a bad leaving group because you're leaving as a negative thing. It's also a strong nucleophile. Your hydroxide is a strong nucleophile, so why would it leave, right? So let's look at what we call good leaving groups. Things like iodine, bromine, chlorine, or neutral water. Notice this has to be protonated first. Neutral water is why it's a good leaving group. And if we look at the pKa's of the conjugate acids, which is the protonated form of the leaving group, we see a trend. That as the pKa goes to less and less acidic, it makes them worse and worse leaving groups, okay? So that's just an extra, if that helps keep it in your mind, go ahead. Don't worry about remembering this. I'm just showing you why it works, okay? So that's why we have iodine, bromine, and chlorine, because those are more acidic than fluorine. So that means these are better leaving groups than fluorine, okay? Hydroxide is a bad leaving group because it's an anion. These are also very bad leaving groups because they're anions. So we would consider these very limited in use, but look at all these up here, the bromine, iodine, chlorine, and a protonated alcohol. Those are great leaving groups for our system. Okay, so, and this is a review of what we did with the SN1, SN2, one step versus 2 steps. And then there's actually a thing here about those benzylic things. We're not actually gonna do that in this test. That's specifically something we're gonna add when we talk about benzenes. Okay, so don't worry about this except for the definition of non-nucleophilic base, which means bulky or hindered. And then this is kind of another way to review what we think, right? This is also summarized in that same table here, but let me go ahead and talk you through how to use this one. When we have our tertiary alkyl halide, think that we are going to try to form a carbocation unless we have an opportunity for there to be an E2 elimination. But it'll never undergo an SN2 because it's just got too much stuff on it, okay? So, but if you have a strong base, you can pull on the hydrogen first before that carbon halogen, or that carbon leaving group does. With the secondaries, that's the one where you can actually do all 4 of these mechanisms. And it's all about how strong or weak your base is. If it's a very weak nucleophile, very weak base, it's going to wait for the carbocation. If you have a strong sterically hindered base, it can actually do the other reaction. It has to pull off an E2. It has to do that bimolecular elimination reaction. And if you have a strong nucleophile or base, you'll get a mixture. There's actually going to be maybe 50-50 because some of it's going to substitute and the other one's going to pull off the proton. So secondaries are the ones to look out for. And then the other thing to remember, and we talked about a little bit, is in a protonated solvent, carbocations are more stable. Therefore, they are favored. In a non-protic or aprotic solvent, they are not stabilized and they are less favored. Okay, that's the last thing about SN1 and SN2 to remember. Okay, and so that is what we've learned in chapter 7. All right, questions. I'm gonna stop sharing and answer questions. So hopefully everything you just heard sounded familiar. And some of the things you heard said, oh, I probably need a little more work on that. Or I know a lot about that. So I think that is going to, this will give you an idea of where you need to, where your strengths and weaknesses might be and where you need to focus first on your study. And so now I'm going to open up to any questions, format questions, chapter questions, homework questions you didn't quite get.
Yeah, so Professor, there was on the homework question that we had for the past one, it was like a combination of this and this makes what, and that's really broad, so let's probably pull it up and tell you that before I. So it's the one where you've got so on chapter 6, I think it was question 5, and it says like an equal mixture of B and C would be optically active, equal mixture of A and B would not be optically active, and I was really confused on that one and where questions would be asked on the test about it.
Okay, so the key there on that homework question, now we're in review, is, okay, one of the things we learned about in optical activity, right, is that when you look at a compound and it's R or S, right, and you actually measure its optical activity, it's going to rotate light in one direction. So if it's pure R, it's going to rotate light in one direction. Okay. The S version of that exact same molecule is going to rotate it equally in the opposite direction. So let's say compound A, that's R, goes to the right 50 degrees. Okay. Now compound A, that's S, goes left 50 degrees. All right. So if they're pure, but if you mix them together such that one's trying to rotate one way and one's trying to rotate the other way, then they cancel each other out and it's not optically active.
Okay, and that's all based on R and S, correct?
But the question could also say, I have this compound that rotates light 100 degrees and this compound, and it might not be chiral. So by mixing them together, you're only going to see the chiral activity.
Okay.
You have to pay attention to, are they both chiral? Now, you could have two different chiral compounds, and one's going to go 20 degrees this way, and one's going to go 30 degrees the same way. Well, you're going to measure 50 because they're both going to add to it. But that's a subtlety we're not working on. But the big key thing is if you have a 50-50 mixture of the ones that rotate oppositely, they're going to cancel each other out.
Okay, that makes sense. I appreciate that.
Okay, great. So, and yeah, on the homework questions, I try to make them a little harder than the exam questions because you have some time to kind of look at them and think. Here, I want you to, think of them as the hardest end of the questions.
Professor?
Yes.
Is the exam going to be timed just in the time frame of class?
Yes, you will have from 12:30 to 2 p.m. to take the exam. It'll open and close, and you have that total of an hour and 30 minutes.
Great, thank you.
There are 35 questions. So don't like hang out for 30 minutes and start your exam, because that will give you 30 minutes less to take the exam. Okay. So I'm targeting 35 questions, roughly, 5 questions per chapter. Some of them are kind of, more than one chapter, like naming a compound might go over 2 or 3 chapters, but so you get the idea that that's approximately where we're going with this. Okay. Okay, so what I'm going to do now is I'm going to go ahead and stop recording, and you can hang out and ask questions if you want, and then I'll post this as my review as soon as we're done here, okay?